What's going on, everyone? Steven here. Today I'm going to teach you how to create health regeneration in a game that doesn't have it. Now this tutorial is inspired from someone who left a comment saying they thought it would be cool if, for enemies in this game you could give them health regeneration to make it more challenging. I thought that was pretty cool. I decided to do this in the context of the player because it's easier. In most games these days that I run across, enemies have shared instructions that they use. So to keep track of each of the individual instances of an enemy and then apply health regeneration to that enemy or single them out, that's very complicated, I guess you could say. Expect to write a lot of assembly if that's what you chose to use for that. So anyway, long story short, you can apply this very same stuff to that if that's what you want to do. So it's just a difference of finding the right memory addresses and perhaps the instructions that you base your code injection on. And yeah, so the first thing is you want to find your health address because that's what you're going to be watching the whole time so that you know when you want health to start regenerating, or stamina, or gold, or just whatever. You can apply this to anything that you want to increment, or decrement, or change in some way, whatever. All right, so we want to find our health. I've gone ahead and I've found health, and then you want to find your max health. So a lot of times max health is in the same region, very close by to your current health. So when you find health, you can right click and say browse this memory region, and that'll be down here. Up here is your disassembler. You can right click display type and choose whatever type your value is. I'm going to say 4-byte decimal. And here we see 50 and 50. Let's go up one. There's a 50 here. So you just have to figure out what's what. If it's, 4 bytes, plus 4 bytes, minus 4 bytes away from whatever, right? So once you figure that out, then what you can do is pretty much always compare your current health to max health. We're going to create a thread. So a thread is kind of like a process that just, it runs. We're going to create a thread that continuously runs, watching health. And if it's below max health, then we'll increment it by 1 every 2 seconds. That's what we're going to do. All right, so I think if we Control-C, Control-V here, and we add 4 to this, so 1C, we've got the 50 there. Let's just say that's max health. Say OK. This is just for you to keep track of. Okay. So now what I'm going to do is I want to see what accesses health. I don't want to see what writes to it, because the first script I'm going to create, in which we keep track of our current health address, I want that value to populate as quickly as possible. So when I enable the script, I want to be able to then enable the CreateThread script that we're going to make and have that work. So basically what I'm saying is, if we look for what writes to this address, we may have something pop up, which we don't. So what that means is we need to get hit or something like that before our health will populate in the script that we run or want to run. So instead of that, find what accesses it. So we'll find things that read from this address as well. So this instruction pops up. That's good. It's running like crazy. This means that as soon as we enable the script that we're going to create to, copy base address to, we'll create our own pointer to it essentially. As soon as we enable that script, it'll happen, right? So the only problem is that here we have this instruction. This is what we wanted to find. Okay, let's go show disassembler. And let's see, it's probably down here, memory view. There we go. So here's that instruction. I'm going to stop this and close it. Now, we'll right click on this and say, find out what addresses this instruction accesses. there is a bunch here, and as you continue through the game, there are more and more and more. All right, so that's a problem insofar as we can't just directly do something with this instruction, right? We have to differentiate something, figure out what's what here. So I'm going to close this for now and stop this. And so I'm going to change my current health value and see it happen here as well. So I'm going to go 21. See how this one changed? So we know that this is our current health. All right, this address is 1.8, this one's 1C, but here we see 1.4, that's 5.0. So let me change this to 1.4 instead. That's probably max health. And so now what you can do is do Control R, which will show you your register states. And what you can do is look at your registers for some value that is different in each of these. You can choose random ones. You can go, however many of these to get your sample size. And you just look through these, and we see that RAX here has a value that changes. So does RDX. All right. So let's just try picking RDX. And the first one that we did was our health, right? So we can say if RDX is 8.6, then maybe that's the right address that we want to, copy over to the pointer that we make to the health address. Okay. Another thing that you can do is select however many you want as a sample, and then right click and go open dissect data with selected addresses. You can just click OK through all this. This is the structure dissect tool, and you can go look at all these offsets and see if there's something that differentiates your values. All right, and in this case, look, it wrote the same address for whatever reason, so then you might have to manually copy and paste in certain ones, provisioning for the offset that it has from the instruction. So let's bring back up memory view again, and here. So here you'd have to calculate what the offset would be that it's automatically provisioning for here. It looks like there's something that bugged out, because we should have different addresses in here for each thing. Anyway, that's for another video. But what I like to do personally is just have a quick glance, do that Control R thing, look at the values in registers. Cool. So we saw that RDX, and the one we're interested in, has 8.6. All right. So now what we can do is, let's bring up the memory viewer on this instruction. Okay, so we want to jump. We're going to jump because we're going to want to allocate memory and do a compare, check some things. So we don't want the jump to fall on this ret, because if we ret up at the point that we're going to jump to, then buggy stuff is going to happen. The game's probably going to crash. So 5 bytes is typically required for a jump to new memory where we're going to allocate it at. So that would be 1, 2, 3, 4, and then 5. Because that falls on the ret, like I said, we don't want to do that. So let's go up an instruction, and we'll start the injection here, which means 1, 2, 3, 4, 5 bytes will be needed for the jump, and then we will NOP 2 additional bytes. All right, and that happens auto-magically for you when you go Tools, Auto Assemble, Template, AOB Injection. And we'll say, well, you know what we can do is copy this, and then we can say OK. We'll say get health. All right, and then instead of doing the AOB scan, we can comment that out, and we could say define get health as this. All right, so we're going to reference that exact offset, all right, to find that instruction. So it's quicker than doing the scan, but not quite as reliable. If they patch something around in this area in a game update, maybe the byte signature stays the same, but the offset will change. So you know. Anyway, I'm going to get rid of that, and let's see, we're going to allocate new memory, keep all that the same. So I'm going to add a label of original code, and then I'm going to change this to original code. All right, so that is our original code that we're going to be coming back to at some point. And then I'm going to put code here. All right, so now what we can do is we are going to want to create an address to store the base address that we can use for writing or watching current health. All right, so in addition to alloc new mem, we're going to alloc, whoops, let's see, let's do, I don't know, health base 8. And now we're going to register a symbol for that. You don't always have to do this. You can do just global alloc. So it would be global alloc health base 8. I have issues with that sometimes, and I'm trying to figure out exactly why that is. So in the meantime, if you have the same kind of issues like your script won't enable if you use a global alloc, just do the alloc and then register the symbol health base. All right, and then what we can do is health base, we'll initialize it. DB, we'll declare quad actually 0. Okay, so now that we have that ready, we know that at this point we're going to want to see if RDX equals 86, right? RDX 86. So what we can do is first push F to preserve the flags register. Then we can compare EDX to 86, right? We'll jump if it's not equal to original code. So if it's not 86, if it's not the one we're interested in, just go back to original code and do what you were going to do. Otherwise, since we have this sort of, RCX plus RAX times 4 plus 20, this is a little more of an advanced calculation of a memory address. So we'll probably want to use LEA, load effective address. And what LEA does, let's just say, let me do this, LEA EAX. We'll copy this just so I can show you the difference. Okay, if you do move, it's going to look in this memory address that it calculates. Okay, it's going to look at the value inside of that memory address and it's going to put it here in EAX. What this is going to do is the memory address that's calculated here, once you get done adding this offset and multiplying RAX by 4, blah, 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 whatever that memory address is, that's going to be put into EAX. So move moves the value from within the memory address that's calculated. LEA moves the address itself that's calculated here into EAX or whatever. All right, so that's the difference with those. All right, so that's original code. So I'm going to use RBX. So I'm going to push RBX to preserve that. All right, then I'm going to do LEA, EBX, and let's do, let's see. So if we look at this instruction here, RCX plus RAX times 4. So at the time that this was ran, RCX has this value in it, plus RAX, which is this, times 4, whatever that is, plus 20. All right. So what we could do is, so that we have this RDX the way that we want to use it, is we could say RCX plus RDX times 4. All right. And then instead of the plus 20 here, I'm going to do plus 20 as an offset from our pointer health base. All right. So this makes it easier to, well, for the LEA that we're doing, right? So I'm going to go move health base, EBX, and then I'm going to pop RBX, okay? And then it'll just flow through to original code, which we can do pop F. So yeah, basically we're doing a check for our address. If it's not equal, go to original code, push RBX to save it. We're going to load effective address here to get the base and not worry about the offset of the exact address. Okay, you could have done we could have done the plus 20 here, right? But the plus 20 is going to take us like exactly to current health. And then from that, what you could do is, as a memory address here, we could say health base or base health, right? If we did the 20 or 20 there, then we could say this and say health for whatever. Okay, health base. Got it backwards. Health base. Okay, and then what we could do for max health is go copy, paste, and then we could say -4, right? Because we've identified that max health is 4 bytes away from health, like -4 bytes. Okay, so you could say -4, but I'm not going to do that. I'm going to take out the 20, and so therefore we have to provision for that here. So I'm going to say +20 here, and then we'll do actually be +20 here. Which one am I in now? Getting all backwards. Let's see. So perhaps this one will be 24, and then that other one will be 20. Yeah, there we go. Getting a little mixed up here. Okay, so now what we should be able to do is I'm going to close this, close that. We should be good for the time being. Health base, register symbol. We can unregister symbol, health base. We could also dealloc it if we want. Something you can't do with global alloc, which I learned recently. All right, and so let's go ahead and file assign to current cheat table, and let's call this get health address. Let's enable it, and let's call this health. Let's call this max health. Move this here, move this here as well. Okay, so now we are pointing to our health and max health. So I just added these so that we can see them, you know. Change that to 30. There we go, we're good. So now we've found health. And we've done off of this instruction. So the moment we enable this, we get our values there. Okay. So the second part to this is going to be create thread. All right. And like I said, a thread is like a task. We're going to create a thread that's just going to be continually running, watching current health. Okay. So I'm going to just open this and get rid of all of that, get rid of all of this. I'm going to go ahead and say File, Assign to Current Cheat Table. The reason I'm going to do that is because I'll do this to open a script, start doing changes, and click OK. That will apply the changes to the thing that you opened. So I have screwed myself over a number of times by doing that. So anyway, I'm going to close that, and now you can just reopen it here. So the first thing I'm going to do is we need to allocate memory that's going to house our code, our custom code that's going to run in this thread. So I'm going to call this health regen. Just alloc the default amount here. Then I'm going to go ahead and say create thread health regen. So that'll create a thread out of this code, and once we type all our code, all that stuff will be here where this is pointing to. I'll go ahead and register a symbol, health regen. Okay, now we need to create some labels. So of course I've gone ahead and sorted all this out. I'm not exactly doing this off the cuff as if I'm creating this from scratch. So the first thing is a label of check, which is going to be where we check for what our health is. Then we'll do a label called wait, which contains where we're going to sleep. So we don't want the script to be just run, 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 run. You know, we don't want it to really tax the CPU. So we'll create a little bit of a wait in there, let's say 2 seconds. And so, yeah, I'll show you more of that once we get to it. Label end. All right, that's going to watch for whenever we disable the script, then the memory will be freed and the thread will be killed or taken care of by a function called virtual free. You can't just de-alloc memory from a thread. It'll cause your game or application to crash. So finally, I'll register symbol end. You have to register a symbol for end so that disable, once you disable the script, it'll still know where to look for end, which is the enable disable value we're going to be keeping track of. All right. So now that we've got this done, what we're going to do is say health regen. Okay. So this is going to be the entry point of the thread of our code that's going to be stored here. Okay. So the first thing I'm going to do is sub RSP20. Okay, the reason I'm doing this is I'm setting up for virtual free whenever we use that. So there are these things called calling conventions. Okay, I have a bunch of stuff up here that I'm going to be bringing back into the video here. Since this is a 64-bit game, we're using the x64 calling convention. All right, usually you push things to the stack, like in 32-bit, push values to the stack, which will be passed as not variables, as dang it, not parameters, but yeah, I can't think of the word, arguments. That's it. Passed as arguments to functions. Okay, so with this, what you need to do is, we see right here in the Microsoft x64 calling convention, it is the caller's responsibility to allocate 32 bytes of shadow space on the stack before calling the function. So that's the thing that I'm doing right now. Okay, and I'll leave you links to all this stuff below. I'm not gonna like really hash it out because it'll take forever, you know. So just know that that's what I'm setting up for, something later. Okay, then we're going to do a jump to wait. So wait is going to be the place where you know, we sleep for 2 seconds. And so basically, once I enable this create thread the first time, okay, it's going to jump to wait. So I want the little 2 seconds of time to wait there before it checks, you know, the health address and starts doing its thing. All right, you don't have to have that there if you don't want it. You could just have it start instantly. All right, so I'm going to say check, wait. I'm going to go ahead and say end. And then I'll do the same thing here. And for the end, it's really simple. We'll just do dd1 end dd0. Okay, so basically, as we go throughout this, it's going to be checking this value, and if it's 1, if it becomes 1, then it's going to kill the thread and free the memory. Okay. So in check here, I'm going to say move into RAX. All right, so this is a funky thing in the CreateThread scripts, is you can't just reference a memory address like this. Or let's say +24. You have to actually have the double brackets here, even if there is no offset. All right, so yeah. So we're going to say move current health into RAX. Okay, so let's see, actually, which one is current health? +20. Actually, I'm sorry, 24 is right. Right, yeah, we do want max health. We're moving max health into here, not current. Because what we're going to do then is compare what's in current health, health base plus 20, to max health. Okay, and unfortunately you can't compare what's in one memory address with another, which is why I'm first moving this into RAX. Okay, here's another thing. You don't have to worry about like initially pushing the values and registers to the stack to preserve them when you're doing a create thread like this. You might have to, depending on what your code is, but you can think of each thread as having its own registers to do its stuff in. So this thread that's running basically has no awareness of the registers or the states of registers for any other thread. All right. So me moving stuff into RAX and doing all this stuff here has nothing to do with like the main thread of execution or any other execution that's going on. Okay. So we can freely reference stuff like this without preserving it, you know, at least in your initial thread of execution. Okay. Okay, we're going to compare what's in current health with max health. All right. If it's equal, I'm going to jump to wait. So jump if equal to wait. So what that's saying is, you know what? These two things are the same. I don't need you to just keep spinning and check. You know, if current is equal to max, jump to wait. And so in wait, the first thing that we're going to do is move into RCX. All right. This is 2 seconds. Okay. And then we're going to call sleep. We're not going to jump to sleep. We're going to call sleep because we want to return back to this point. Okay. So then we will compare. All right. The value and end with 0. We're going to jump if equal to check. So what this does is once something comes into wait, we move into RCX, which again, this is part of the 64-bit calling convention, is that it doesn't take things off the stack until much later. Bring this back over. Okay, it uses registers RCX, DX, R8, R9 for the first 4 integer or pointer arguments. Okay, so whenever you want to, you know, call or jump to a function, you need to put your values in these registers in this order. Put your arguments in here. So that's why I'm going RCX. Okay, so we move that into RCX, then we call sleep. And sleep runs, and basically it sleeps this for 2 seconds. Now you wouldn't want to do this in the middle of execution of like the regular or the main thread that the game is running, because that would cause the entire game to sleep out of context, which will probably crash your game. So since we have this thread running this individual thread of execution, we're okay doing this. This is like a thing on the side that's watching the main game or watching something from the main thread of execution, if that makes sense. Specifically, we're having it watch a memory address, right? Okay, so we jump if equal back to check. It checks max health, checks current health, you know, that whole thing. Okay, so if current health is less than max health, let's just increment current health by 1. So inc or increment is an instruction that the CPU knows. It says add 1 to this thing. So really simple there. I'll do a follow-up video showing you if this is floating point. You can use the FPU. You could use XMM registers with SSE instructions perhaps if you wanted. So anyway, after it increments, we're going to jump to wait again and just have it wait for 2 seconds before it does this check. Otherwise, it's just going to be really spinning up your processor. Okay. So now that we've got that done, we're at this point in execution here. So I would call this something like free memory and kill thread, right? If I were to label this section that's going to be moved into. But since I'm not referencing this from anywhere, I'll comment that out. But I like to keep it there as sort of a frame of context for me. So now what I'm going to do is add RSP 20 or 20. And this has to do with this whole thing. Again, I'll leave a link and you can read into why that's doing what it's doing. But we're preparing arguments to be passed to virtual free. So remember this whole thing here about using these registers in this order. I have here x64 architecture. Nope. This one here. Okay. RCX first integer argument. RDX second, third, fourth, right? So it's there specifically on Microsoft's site showing you that. Okay. So now what we're going to do is move into RCX, health, regen, and you're probably wondering like, how are you knowing to move these things in these places? Okay, I'll show you in just a second here. We'll sub RDX, which basically makes your value or your register, it zeroes it out. So subtracting a value from itself equals 0. This is a mnemonic that most CPUs recognize to mean just make this register equal 0. You could also say move into RDX 0. This is a more expensive instruction, meaning it takes more cycles to process, or you could do XOR RDX, which makes that register equal 0. Also another highly recognized mnemonic for that. So basically we just want 0 in RDX. Okay, so take your pick. Now we'll move into R8D, all right, this value. And then we'll say jump to virtual free. Not call, we want to jump there, because what's going to happen here is the memory is going to be freed, the thread's going to be killed. We don't want to come back to this spot at all. So when you call something, all right, your return address is placed on the stack, and then all the stuff happens, and then it tries to return to where you called from, to the caller, right? We don't want to do that. We just want to jump. Here, you've got all these arguments. Take these, go here, and just let that do its thing and don't come back. All right? So the reason I knew to pop all this stuff here is, first of all, there's a guy named Parkour Penguin over on the Cheat Engine forum. I learned all this stuff essentially based off of his template on this. So thanks to that guy. All right, so let's go to virtual free. So you could Google for the virtual free function, and then you'll come across the MSDN page here or Windows Dev Center, and it tells you basically the parameters that you need that this function requires. All right, so you've got address, size, free type. Now, this stuff used to confuse me when I would see like LP and DW, like what does all that stuff mean? They're part of coding style conventions from like back in the day in Win32 programming, and they persist today. So DW means D word, L long, LP long pointer. So if you see those like lowercase things like that in front of the name, you can just go to this coding style page and see. It's just a way that you can quickly identify, oh, hey, this variable or whatever, it's a long pointer, it's this, it's that, whatever. Okay. So let's go back here to our script. Move this over here. I should be able to see both of these things. Okay. So here we're moving into RCX, which is the first. This is the register with the first parameter that's needed, or argument rather. and it needs a pointer to the base address of the region of pages to be freed. So health region, that's what we allocate. We created a thread based on this that we allocated, this page of memory. So that's what we want to release. Okay, the next one, DW size, the size of the region of memory to be freed in bytes. You may be wondering, why is that 0? Well, if we keep reading here, if the free type parameter is mem release, this parameter must be 0. So if you go look down at this memory release here, okay, we do want memory release. If you read through this and read through this, you'll see that what we want is release. The value is 8000, hex 8000. So that's why we, in the third here, into R8, we put 8000. So because it's 8000, it's mem release. This one, DW size, the second one, must be 0. All right, so we have satisfied virtual free with these arguments, pass it, and then our thread will be taken care of, the memory will be freed. Okay, and finally in disable, what we can do is say unregister symbol end, and then we can unregister symbol health region. All right, so now I'm going to say OK and move this back over here. Now I'm going to call this health regeneration. All right, so if all goes well, I should enable this, and then we should start seeing health count up. Look at that. Every 2 seconds, we have 1 added to health. So we've given ourselves health regeneration. So in games where you don't have health regeneration at all, whether it's from a potion or otherwise, now you can do something like this to add it in. All right. So let's see, just some parting words so far. We went over that stuff. Some of you might have been confused by R8, R8D, right? It's just the lower 32 bits. R8 is a 64-bit register. R8D is the lower 32 bits, and so on and so forth, right? Now, this is the 64-bit way of doing this. I'll be back with a 32-bit game to show you kind of how this would look in that context, using calling conventions, x86 calling conventions. And, you know, you can see how they compare and contrast and start getting used to that if this is something that you're wanting to start doing. So anyway, I know this was a little bit of a long video, but I hope you enjoyed it. Feel free to leave some comments, let me know your thoughts, and go check out my other ELEX videos if you're into this game. Did a bunch of cheat videos on that, and some other just generic cheat engine tutorials if you want to learn about this stuff and don't know what's going on. So anyway, thanks so much for watching. Give me a thumbs up if you enjoyed it. Don't forget to subscribe, and I'll talk to you all in the next video. Take care.